Hey guys, Mr. Hallman here. Welcome to another week of polynomial functions. Last week we talked about the factor and remainder theorem. And if you recall, both of those basically told us how to figure out whether a linear binomial was a factor of a larger polynomial function or not. And we used synthetic division and substitution in order to help us determine that. This week what we're going to do is we're going to look at actual polynomial functions, and we're going to look at how do we solve them. And again, I'm going to introduce a couple other theorems and show you how we use that in conjunction with the stuff that we talked about last week to solve these larger functions that we haven't worked with necessarily in the past. So the first thing we're going to look at today is what we call the rational roots theorem. So the rational roots theorem basically tells us how do we determine what rational numbers end up being roots or solutions or zeros for specific functions. So it says here, let P be a polynomial function with integer coefficients. That means positive or negative whole number coefficients, and it's in standard form. So from largest exponent down to the smallest one. We know that if some rational expression P over Q, which has been reduced, is a root of P of x equals 0, then that tells us two things. First of all, the P, or the numerator, has to be a factor of the constant term of the larger function. So that means whatever the last number is in the function, the factors of that value represent the numerator. And Q, the denominator, is going to be a factor of the leading coefficient of P. So when we say leading coefficient, we mean the number in front of the largest degree term. So we're going to be able to determine what numbers end up being roots or solutions to a polynomial function using this theorem and by constructing these fractions. Let's take a look at how we do that. All right, before we start solving, let's go through the steps to actually figuring out what the roots are. There's 5 basic steps. First, as you saw, we're going to be dealing with rational numbers. So we're going to have to come up with what are the possible solutions. And the first thing we're going to do is we're going to figure out what are the P values that we might be able to use. Again, P represents the factors of the constant term in the polynomial. Second thing we're going to have to do is figure out what the Q values are. And again, those are the factors of the leading coefficient of the polynomial. Once we've generated the list of the P and Q values, we're going to take those and we're going to put them into fractions, P over Q, to determine what all of our possible rational roots are. One of the things that's different about solving a polynomial function versus anything else that we've ever talked about is that it's not necessarily a do this and then you get your answer kind of process. We're actually saying here's a function and there's literally an infinite amount of numbers to choose from that we could have as possible solutions. So this is how we whittle that down to a specific value or a specific set of values. We're actually going to cut it down to maybe 4, 5, 6, 7, 8. It all depends on what our solution or what our function actually is. So we're going to have to generate what are the possible roots, and that's what we're doing with the P over Q values. Once we've created our list, then we're going to test them. And we're going to test them using one of the methods that we used last week. We're going to use synthetic division. Because when we're testing, we're technically using our factor and remainder theorems. We're taking the synthetic division, we're seeing do we end up with 0. If we end up with 0, that means that's our remainder. So yes, it's a factor. And the fifth step is once I've found one of those values to work, what we'll see is that the polynomial oftentimes can be simplified by factoring. And then that allows us to figure out what the other roots are. We're going to go through some different examples where we have to do each of these steps. Some of them we can cut out, and we'll talk about those as we go along. So let's look at our first example together. All right, so let's look at our first example together. It says find the rational zeros of P of x equals 12x cubed minus 8x squared minus 3x plus 2. So what we're going to do is we're going to follow that process that we just talked about. We want to generate our list of rational numbers that might be solutions to this equation. So the first thing we're going to do is generate our list of P values. Remember, the P values are the factors of our constant term. So the p-values come from the factors of 2, which means that they could be either plus or minus 1 or plus or minus 2. The q-values are the values that are going to be the denominator, and they are the factors of the leading coefficient, which in this case happens to be 12. So that means we have q-values that could be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. And then what we need to do is we need to generate the actual list of p over q values. So now that I have those, I'm going to generate p over q, because these are going to be the numbers that actually could be solutions. So the easiest way to do this is to pick one of your p values and start with that as the numerator and put that over all of your possible denominator values. So I'll start with 1, and we could do 1 over 1, so we have plus or minus 1. Then 1 over 2, so plus or minus 1/2, plus or minus 1/3, plus or minus 1/4, plus or minus 1/6, and plus or minus 1/12. We're going to do the same thing with the second factor for p, which is 2. So we could also have plus or minus 2 over 1. Then we have 2 over 2, but 2 over 2 is the same thing as 1. So I don't need to rewrite that one. Then I would add plus or minus 2 over 3. And then I get to 2 over 4. But 2 over 4 is 1/2. So I don't need to write that again. 2 over 6, that's the same as 1/3. Don't need to write that. And 2 over 12 is 1 over 6. So this is our final list then of possible solutions. And again, you might be saying, that seems like a whole lot of numbers to choose from. And you're right. When we talk about solving a linear equation compared to this is a whole lot more choices that we have and a lot more that we need to check. I mean, if we check 1, 2, 3, 4, 5, 6, 7, 8, and then we have plus or minus for each of them, there's 16 possible numbers. But again, what we've basically just done is we've said, here's a function, figure out what could be the solution. Out of an infinite amount of numbers, we've narrowed it down to one of these, well, something from this list of 16 values. So 16 compared to an infinite amount, that's pretty good. Next, we would start going through here and we would pick these values and do synthetic division. But we're actually not going to do that right away, because if possible, what we always want to check is whether we can factor first. So check if we can factor. If it's possible to factor the polynomial, then I want to make sure I do that. In this case, when I look at 12x cubed minus 8x squared minus 3x plus 2, if I was going to factor it, I would have to use grouping because I have the 4 terms. So I would put my parentheses here, put parentheses here, change that to a minus, and then I would factor out the GCF from each of those groups. Well, the GCF of 12x cubed minus 8x squared, that would be 4x squared. And the leftover would then be 3x minus 2. GCF of 3x minus 2 is just 1, so I have minus 1 times 3x minus 2. And notice I ended up with the same leftover factor. So I lucked out in this case that I have 3x minus 2 times 4x squared minus 1 now. And as we've seen, when we solve a function, we're always trying to work down to the linear binomials. So I do have one linear binomial here, the 3x minus 2, but I have 4x squared minus 1. Well, that can still be factored because that's a difference of squares. That's the same thing as having 2x plus 1 times 2x minus 1. So now I've narrowed this polynomial down, which was a cubic polynomial to start with of 4 terms. We narrowed it down to these 3 binomials. And remember, we're really saying that this is equal to 0. So at this point, we now would say, all right, these are my binomials, so either 3x minus 2 equals 0, or 2x plus 1 equals 0, or 2x minus 1 equals 0. And we would then go through and we would solve each of those. So that would mean that x equals 2/3, or x equals negative 1/2, or x equals positive 1/2. And we could write our answer that way. We'll also use set notation to write this. So you might also see it written x equals, and we use the braces for the set, and then you can write in the 2/3, and then we would have plus or minus 1/2, because we have both the positive and the negative. So either of these ways of writing the answer would be acceptable. To write out each of the individual roots, x equals, or to use the set notation. So here we generated our list of possible roots, but we didn't actually use synthetic division, we just factored. But if I double check, 2/3 was in my list, plus or minus 1/2 was in my list. Let's look at another example. Actually, before we jump into that next example, let's take a look at the fundamental theorem of algebra. So this unit has dealt a lot with different theorems and how do we use them. The fundamental theorem of algebra is basically the one that allows us to solve any of these equations, and it tells us some very specific information and important information that we use not just now, but you'll use in college algebra all the way up through calculus and beyond if you take math classes beyond that. So here's what the fundamental theorem of algebra tells us. If I have a polynomial of degree n, something that's greater than 1, and it has complex coefficients. Remember, real numbers are technically complex numbers as well. They just have 0i as the imaginary part. That means that there's at least one 0 in the set of complex numbers. So if the degree is greater than 1, there has to be at least one 0 or one solution. And not only that, if I know that it's a polynomial degree n greater than 1, I know specifically that it has exactly that many complex zeros. So whatever the degree is, I'm going to have that many solutions. And it's important to note, this can include roots with multiplicity greater than 1. We'll talk about multiplicity today and what that means, but essentially we're saying if I know the degree of the polynomial, there should be that number of solutions or zeros or roots to the function. And it's always going to be including multiplicity, meaning maybe the same number occurs more than once. And you can see here, I have a picture I took of myself this morning. It was really bright out, so I had to wear my sunglasses. But this is essentially what we've been working to all year to get to this point, that this theorem, the fundamental theorem of algebra, really, when we talk about what are we doing in class, this is the math that we're talking about. This sets up everything moving forward. So let's look at our next example using this to help us figure out how many solutions should there be, and then we'll work through to figure out what they are. Alright, so example 2. How many roots will p of x equals x cubed plus 3x squared minus 25x minus 75 have? Then we want to find the roots. So the first thing we're going to do is we're going to identify the degree of this function is 3 because that's the largest exponent. Therefore, we know that there are 3 roots. So that means when I've solved for my answer, I should have 3 solutions. Might be the same, and I might have a multiplicity, but in general, there's going to be 3 answers. Now we're going to generate our list of p over q values, unless, in this case, it just says find the roots. So if I wanted to take the time to find p over q, I guess I could. Let's do it. P values, remember, they're going to be the coefficients, or excuse me, the factors of the constant term. So in this case, our p values would be plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15, plus or minus 25, and plus or minus 75. And our q values are going to be the factors of the leading coefficient. Well, our leading coefficient in this case is 1. So that's just going to be plus or minus 1. So really, I can actually get rid of the q here, and I can just say that this list of p-values actually is the same as my p over q values. And I would go through and I could test using synthetic division, but wait, always check and see, can we factor? And again, x cubed plus 3x squared minus 25x minus 75. Can I factor there? Sure, I'm going to use grouping again. So we put in the parentheses. That changes to a plus now. So now we have p of x equals, and actually not p of x, let's get rid of that. We're going to make it 0. We're saying, when is this equal to 0? Well, if I factor out my GCF from the first quantity, that would be x squared times x plus 3. And then minus, out of 25x and 75, I can factor out 25 times x plus 3. So now I have 0 equals x squared minus 25 times x plus 3. So my linear binomial here of x plus 3, I'm done with. The x squared plus 25, however, we have to keep going. That's another difference of squares. So we get x plus 5, x minus 5, and x plus 3. Now I'm down to 3 linear binomials. Again, I should only have 3 roots. So that's what I'm going to end up with. We would say x plus 5 equals 0, or x minus 5 equals 0, or x plus 3 equals 0. Which then means when we solve them, x can equal basically plus or minus 5 from our first 2 equations. It could also equal negative 3. That would be our final answer. Again, we didn't have to do the synthetic division. Let's look at another example. All right, so in example 3, we have x to the 4th minus 11x squared minus 18x minus 8 equals 0. And we're going to see that there's a couple of things that we have to worry about here. Let's follow our process. First step, we find our p-values, which again are going to be the factors of our constant term. So in this case, our p-values end up being plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Our q values should be the factors of the leading coefficient. But if I look at my first term, the leading coefficient ends up being 1. So that means, again, I could put all those over 1, but really, it's just going to end up as the same thing. So my p over q values here happen to be 1, 2, 4, and 8. So I can't, I'm good with my possible solutions. It's going to be it will have to be from these 8 numbers. Next, we would look and see, can we factor this expression? And there's 2 things that indicate to me, no, I can't factor it. One is that this is an x to the 4th. When we had x to the 3rd, it may have worked, but there's no way that I'm going to be able to group here and possibly get the same values, because these would have x squared as a GCF. I'd still have an x squared. This does not. The other thing is, I can tell 1 and negative 11, negative 18, negative 8, they don't share common factors. So I'm going to have to go through the process that I outlined before, which is now I'm going to test these numbers here using synthetic division. And since we're going to be doing synthetic division more than one time, I'm actually going to change the way I write it. I'm going to make a little table here. And above the line, so over here, I'm going to fill in my coefficients like I normally would for synthetic division. So I would have 1. There's no x cubed term, so I have to put in the placeholder 0. Then negative 11, negative 18, and negative 8. Next, what I'm going to do is I'm going to plug one of these roots in. So I'm going to pick something from here. Doesn't matter what. Let's say we choose 1. So I'm going to modify the way I go through and do this. again, the first coefficient would always come down. So 1 comes down. And now we're going to take this times that. So 1 times 1 is 1. And I'm going to add it with the 0. That's still going to be 1. Do the same thing. 1 times 1 gives me 1 plus negative 11. That gives me negative 10. Then we do 1 times negative 10. That's negative 10 plus negative 18. That's going to give me negative 28. And then 1 times negative 28 is negative 28 plus negative 8. That gives me negative 36. Did I end up with 0? No. If I had, that would have been a root. So this one doesn't work. So I know for a fact 1 is not a possible root. Let's try a different one. So maybe I try negative 1. Again, we follow the same process. This 1 comes down. So we'll do negative 1 times 1, which is negative 1, plus 0 gives me another negative 1. Then we're going to take negative 1 times negative 1. That's 1 plus negative 11. That's negative 10. Well, this is not great because it looks like we're starting off the same way. But now, negative 1 times negative 10 is 10 plus negative 18 gives me negative 8. And then negative 1 times negative 8 gives me 8 plus negative 8. That gives me 0. Yes, that is what we wanted to end up with. So what that means is if negative 1 works here, I know that this actually breaks up then into x plus 1. And then these numbers are the coefficients of the remaining terms. So I would still then also have x cubed minus x squared minus 10x minus 8. And now my hope would be that I can factor this. Sadly, I cannot factor this. So I have to go through synthetic division again a second time. But now I'm dividing this polynomial, the x cubed minus x squared minus 10x plus minus 8. So that means here I'm going to have 1, negative 1, negative 10, and negative 8. Now, I've already shown in this case that 1 doesn't work, so I'm not going to test 1 again. But I did find that negative 1 worked. So maybe I want to try negative 1 again to see if there's a possibility of there being a multiplicity. So I'll take negative 1, and I'm going to go through the process. Bring down the 1. Negative 1 times 1 is negative 1. Plus negative 1 gives me negative 2. Then I would take negative 1 times negative 2, which is 2, plus negative 10. That gives me negative 8. Then I would take negative 1 times negative 8, which is 8, plus negative 8. That gives me 0. This shows that negative 1 worked again. So now I have, instead of just x plus 1, I actually have 2 of them. Or I have x plus 1 squared. The leftover would be x squared minus 2x minus 8. And at this point, now I have something that I can reverse FOIL. So I'm going to take this, keep it as x plus 1 squared, but I'm going to break this up into x and x. Sign tells me I need to do 1 positive and 1 negative. And I need factors of 8 that would subtract to give me negative 2. So that's going to be minus 4 here, but plus 2 here. And just check, negative 4x, positive 2x, that's negative 2x. So now I have my solutions. I would say x plus 1 equals 0, or, again, x plus 1 equals 0, or x plus 2 equals 0, or x minus 4 equals 0. Once I've done that, I now show that x can equal negative 1, and not just once, but I had 2 of those binomials. So I'm going to put in parentheses 2x to tell me twice, or 2 times, negative 1 was a root. We also have negative 2 as a root, and we have positive 4 as a root. And you might be saying, well, wait, that's only 3 solutions. I thought because this was degree 4 that there should be 4 solutions. And there are. I have 4 and -2, and I have -1 twice. So that would be 1, 2, 3, 4 solutions. I know this process can be a little bit longer, so we're going to go through 2 more examples together. I would encourage you to at least try one on your own. Let's look at our next one. All right, after reviewing, I realized this is our last example. So here's what we're going to do. For example 4, we're going to find the rational roots and the multiplicity of p of x equals 3x to the 5th minus 15x to the 4th plus 18x cubed plus 12x squared minus 24x. So the first thing that I notice is the degree. In this case, it's a degree 5, which tells me that there should be 5 roots. So I'm looking for 5 solutions to this function. The other thing I notice is when I try and generate my p over q values, I notice that for p, that should be the constant term. There is no constant term here. It stops at -24x, which means if I have an x in every single term, there's a GCF, and I need to factor that out first. So what I'm going to do is I'm going to keep this set it equals 0, and I'm going to factor out my GCF, which I know it's going to have x. And if I look at my coefficients, we have 3, 15, 18, 12, 24. Looks like 3 is also part of my GCF. So now I have to factor that out, and the leftovers would be x to the 4th minus 5x cubed plus 6x squared plus 4x minus 8. All right, and I cannot factor out another GCF. And when I look at this, I notice that the leading coefficient now of x to the 4th is 1. So I'm not going to use any q values other than 1. I simply need to identify what the possible p values are. And that's going to be the same thing as p over q. Remember, those are going to be the factors of this term. So we should have plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So if you would like to pause and try this one on your own, go ahead. Otherwise, I'm going to work through here. We're going to have to do some synthetic division. So let's set up our division here because that's not going to factor nicely for me. So I'm going to have 1, then -5, and then 6, and then 4, and -8. And I'm going to just start trying different values. So maybe I'll try 1. So the first coefficient comes down. 1 times 1 is 1, plus -5 is -4. 1 times -4 is -4, plus 6 is 2. 1 times 2 is 2, plus 4 is 6. 1 times 6 is 6, plus -8 is -2. 1 is out of the party. Didn't work. All right, I'm going to try, I could try -1 if I wanted to. Let's do it. So we'll try -1. Bring down the 1 again. So let's see. -1 times 1 is -1, plus -5 is -6. -1 times -6 is 6, plus 6 gives me 12. Let's see. -1 times 12 is -12, plus 4 is -8. And -1 times -8 is 8, plus -8, hey, that gives me 0. I ended up with one that worked in this case. So I know now that 0 equals 3x times -1 works, so that corresponds to x plus 1. And then the leftovers, x cubed minus 6x squared plus 12x minus 8. And if I look at the x cubed minus 6x squared plus 12x minus 8, I would check to see, could I factor that? In this case, I can't. So I'm going to have to set up another synthetic division here. So let's jump down here. So now my coefficients across the top should be 1, -6, 12, and -8. Again, I saw that -1 worked the first time. I'll try it again. I always suggest trying the same root to make sure that there isn't a multiplicity. If there is, this will show me right away. So I bring down the 1. Let's go through. -1 times 1 is -1, plus -6 is -7. -1 times -7 is 7, plus 12 is 19. This is not going to work out because -1 times 19 is -19, plus -8 is -27. All right, so -1 worked the first time, didn't work the second time. Try a different number. I'm going to try 2. You can pick whatever you want. Let's see. We bring down the 1. 2 times 1 is 2, plus -6 is -4. 2 times -4 is -8, plus 12 is 4. 2 times 4 is 8, plus -8 is 0. There's my next root. So I found that 2 also works. So I come back up here. I have 3x times x plus 1 times x minus 2. Remember, I'm always using the opposite of what I see in the binomial when I do the synthetic division. That's why -1 corresponded to x plus 1, 2 corresponds to x minus 2. The leftover is x squared minus 4x plus 4. And in most cases, we get down to a quadratic here. We're going to be able to factor it. So we'd have 0 equals 3x times x plus 1 times x minus 2. And x squared minus 4x plus 4 actually turns out to be a perfect square trinomial. It's x minus 2 times itself. So really what we have is 0 equals 3x times x plus 1 times x minus 2 to the third. So that means we could have 3x equals 0, and I have to have 3x equals 0 because it has this variable. So I have to set that equal to 0. Or x plus 1 equals 0. Or, I'm not going to write it out 3 times, but I would have x minus 2 equals 0. So when I solve, let's see. I forgot what I was writing here. So now we have x equals. Well, 3x equals 0, that comes from 0. The x plus 1 equals 0 would give us -1. And the x minus 2 would give us 2. But again, I had 3 of those binomials. So really, 2 is a root 3 times. So if I count 1, 2, 3, 4, 5 roots, which is what we should have ended up with, there's our answer. So this week you'll have some practice on IXL where you're just going to be identifying P over Q values. You also have a short worksheet where you're actually going to be doing this whole process. If you have questions, don't be afraid to reach out to me on Schoology or by email. We'll have our weekly Zoom meeting on Wednesday. And otherwise, anything else you need help with, just let me know. I hope you guys are doing well. I miss you, and I hope to see you soon. Take care.